Thank you very much. Thanks, Brett. And thanks, Jason. It was great to hear your presentation for the second time. Yeah, and I feel like I got a lot more out of it this time too. So, hi, my name is Marcus Strang, and I'm an environmentally sustainable design engineer based in Melbourne, working at Green Consulting, where we specialize in passive house buildings for design as well as certification across many different types of typologies around Australia. Um, I'm also just coming towards the end of the first year of my PhD candidature, where I'm looking at the pathways towards net zero energy for engineered timber multi-story buildings in subtropical and tropical climates. And so this presentation is about talking about some of my preliminary results, um, where I'm looking into some of the background of the building physics of control layers and the hygrothermal behavior, which is the air, moisture, and vapor behavior of mass timber, as well as putting forward a framework for analyzing climate-specific durable designs, and then going and looking at a well-received case study building that was constructed in a temperate climate in Australia, and transferring that same design to a subtropical climate and looking at the climate-specific design required to still meet the passive house standard in Brisbane, and then just giving some recommendations at the end. So over my research, I've identified a number of knowledge gaps, and the one that I'm kind of looking at the most in this presentation is the long-term durability and how the CLT assembly performs in high relative humidity and in tropical and subtropical climates. However, I'm also looking in my research at how adhesives in the CLT itself behaves, as well as how to best construct a building to increase the drying out ability and reduce the amount of moisture that comes in during construction and operation and even decommissioning. So the significance of this is that a lot of our CLT designs and buildings have evolved in cold and temperate climates like Europe. And now as CLT and even passive house becomes more popular, it's starting to transfer over to different climate zones like tropical climates and subtropical climates around the world. And due to that, we need to look at how we design these structures, because there's a difference in the building physics. Well, the building physics is the same, but how we design it to increase the durability is slightly different. And so in Brisbane, 50% of greenhouse emissions occur in New Brisbane homes, so it's just purely minimum compliance. And as we build more high performance buildings, this operational energy reduces, and the building material represents a far greater ratio. So we need to start looking at what we build the buildings out of. So just for your information, Australia is able to produce 1 cubic metre of timber from sustainably managed forests every 13 minutes. So we produce a lot of timber that is perfect to use for the structure of the building. So the benefits of CLT that I'm most interested in is its carbon sequestration potential. So when we look at any timber product, the half of the dry weight of that product itself is carbon that it's absorbed from the atmosphere. So that's pretty incredible and a really great way to try and reverse climate change, and also looking at the timber, how it performs thermally as part of the fabric due to its low conductivity, and which reduces thermal bridging effects and the like. Timber also is great for construction, so it's really when you build the assembly in a prefabricated system, that reduces a lot of the errors that occur. You can start building systems to 1 or 2 millimeter tolerances, and when you go out and set this up on site, it goes up significantly quicker than the alternative, which is reinforced concrete buildings. In addition, it's much safer. There's seismic and combustibility performance benefits, and the timber buildings can be very durable when designed correctly. So as an example, this on the right, the Buddhist temple in Japan, is still in place for the past 1300 years. During the conference in Galbadian, just outside of Beijing, I was also very fortunate to have a look at a lot of timber buildings that have been there for many hundreds of years and are likely to be there for the next few hundred, so extremely resilient when designed correctly. So in the Australian construction industry, there is a bit of a knowledge gap when it comes to managing moisture. And this goes for any material, really. But as modern construction now utilizes more and more modern materials that tend to be impermeable, such as metal and glass and impermeable insulation. So this detail here is quite a common detail used in Australia for multi-story panels. So here we have a spandrel panel where it's highly likely that interior moisture gain on the interior diffuses through the insulation and possibly condensates on the metal backpan, which can lead to moisture issues if not considered adequately, as you can always expect a seal to slowly degrade over time. So yeah, so that's something that I'm looking at in the Australian context. So a typical CLT layer detail from Europe will have we'll address the control layers in this way, where we've got the air and vapor control layer on the interior, and that's to prevent any air from infiltrating into the assembly. And then we have the thermal control layer, and that's to improve the energy efficiency of the building and to reduce the amount of heat that transfers out. And then we have the weather control layer on the outside, which is the cladding and prevents the wind-driven rain and wind to ingress into the assembly. And we also have the water control layer, which acts as a redundancy, just in case any rain is getting past the cladding. It prevents it going into the assembly to cause moisture accumulation, which will eventually cause mold and rots and structural deterioration. And so we can see again, yeah, so usually this presentation would kind of bump up slowly when I click it. But so on the right-hand side, we have a European cold climate where I've highlighted the interior wall, and that's where we want to have our vapor membrane to prevent interior moisture from infiltrating the wall system and condensating against any cold elements as it moves outwards. However, on the left-hand side, we have a warm and hot climate, and we can see that the vapor drive is towards the inside of the building, where as any moisture that gets through the assembly cools down and also has the risk of condensating. So we want to have that vapor membrane on the outside to control that vapor flow. So timber itself is actually a really quite impressive material. It has some useful characteristics. So on the right-hand side, we can see this this line here. So it hasn't come up well, but we can see the 50% relative humidity, and that has a diffusion resistance factor of about 80. And so diffusion resistance just gives you an idea. It's a unitless factor, which tells you the amount of its resistance to allowing vapor through the material. However, when we increase the humidity, it actually has a lower resistance, so increased permeability. So in this way, we're actually able to, in some way, control the amount of moisture that goes through the building assembly. And that's because of, on the left-hand side, we can see a section of timber. So due to its porous, permeable nature and hygroscopic, as moisture, you probably can't see my mouse, but moisture will diffuse through the pore. And as that pore builds up with moisture, the pore gets smaller and smaller, and that increases the capillary effect and its ability to transfer moisture. And here is another useful timber property to get your head around, is the moisture storage capacity. So we can see the weight here, and that's how much moisture it's actually able to hold, and then the cup is the safe storage capacity. So the trickle that's coming out is it's diffusing and it's drying out into the drier ambient conditions, whereas the wetting taps represent moisture leaks from the interior or rain-driven, wind-driven rain from the exterior, or leaks around windows and fenestrations. So what we really want to do when we look at durable design is limit the amount of wetting that's occurring and trying to increase as much as possible that drying effect. And on the right-hand side, we can see the unbound towards the upper limits of the relative humidity. We can see the unbound water and supersaturation. So we want to avoid those because these are this is when the timber has so much moisture that mold is able to grow and use the timber as a growth substrate. So without that, it's actually unable to survive on timber because there's no food for it, essentially. So now I'll take you through my case study building. So this is the largest passive house CLT building in the Southern Hemisphere. It's called the Monash Peninsula Gillies Hall, and it's 150 student accommodation units. You can see on the left image that it has exposed CLT panels to the interior, which improves the drying capacity. So I've looked at this building and then transferred it into a subtropical Brisbane climate and looked at the effects that it has. In this image, usually this animation would just be running, and we would be able to see how slowly the moisture dries out over time. For this example, I just put increased moisture into the CLT to simulate a rain during construction, to just watch how slowly it dries out until it'll actually take up to a year to completely dry out. And so this is just to highlight that you really want to control the environment when you're constructing CLT to create that durability. And on the exterior surface layer, that's a critical surface layer, so really be managing that. So I've used ASHRAE 160 as a framework to look at the durability, specifically the mold growth index, to try and keep that below 3, which represents the mold growth visible under a microscope. So on the right are a few graphs where I have external insulation, such as XPS, or it could be even be EPS, or that has a slightly increased permeability. And we can see that when there's external insulation that's impermeable, there's an unacceptable level of risk, and that's the same if you've got internal insulation that's impermeable. So this really shows that that having any sort of vapor barrier really reduces the ability to dry out. And on the bottom, we have permeable insulation such as rock wool, and in that Brisbane climate, it's looking quite okay. So this slide is just to highlight the framework that I've used. So number 1 is in ideal conditions. So this is really not with no redundancy for wind-driven rain or rain events. And you can see that the mold growth is 0. So that's ideal conditions and extremely unrealistic. And then case 2 is if we have increased initial equilibrium moisture content, and so that represents that rain during construction, or increased moisture content during transport or so forth. And we can see that the mold growth index is still okay, but it's going towards the upper limit of what we're looking for. And then when we have case 3, that's looking at just driving rain, and we can see that in this climate, that's actually okay. When as for this specific project, it's able to dry back out sufficiently. And then case 4 is looking at both driving rain and increased initial equilibrium moisture content, and we see that we have an issue as it's over 3. So it's potentially not drying out adequately, and there may be risk of molds and rot in this case. So now I've looked at what can we do to increase the drying potential. And so that's done by increasing the ventilated air cavity, which could be practically done by improving the air permeability of that cladding, although you still really want to make sure no rain is able to get through. And so that reduces the mold growth to 1.7. And then having a more permeable weather resistive membrane decreases it even further. And then for step 3, if you take extreme care of that moisture during transportation and installation, we have a very low mold growth index. So this might be done by putting up a tent during construction to make sure even if there's rain, it all pulls away and it doesn't sit anywhere, or sealing all the edges as they're the most vulnerable sections. So taking some precautions to ensure that there's no increased moisture. Yeah, so now I'm just showing some comparison of some climates in Australia to look at an energy analysis for the whole building. So we can see here, and as everyone would know, the PHVP, for PHVP compliance, we want to limit overheating to less than 10% of the year, which is over 25 degrees. So for Brisbane and Cairns, we can see that our ambient climate is actually already over this 10%. So we're going to have sensible cooling loads. And likewise for excessive humidity, which you want to limit to 20% for thermal comfort. Again, Brisbane and Cairns is way over that. So we're going to have latent heat loads for that. And we can see here that for a number of climates, Darwin and Cairns, and to some degree Brisbane, also has extremely high latent load. So in these climates, which I haven't really assessed in this presentation, you may need to swap the insulation to the interior to ensure that the CLT is on the warm side and not on the conditioned cooled side to reduce the risk of humidity levels. And then, so we're all quite used to this image of the normal passive house principles. So in hot and humid climates, it actually changes somewhat. So we have our windows in which we want to reduce the solar heat gain coefficient to reduce the amount of solar radiation that's coming into the building and increasing overheating. We want to use energy or enthalpy ventilation strategy. And we want to ensure that it's a very airtight building to reduce the amount of moist air that's coming into the assembly. The other two that aren't so applicable to cold climates is looking at external shading and external finishings. And that's to increase the emissivity and reduce the absorptivity of the solar radiation on the fabric. And so here are these same design changes to meet the cooling and dehumidification demands of 25 kilowatt hours per square meter annum. And the reason this is higher than the usual 15 is due to internal heat loads and that latent cooling load, which is not so applicable to cold climates. So therefore we have a bit more of a tolerance. You can see here that the reinforced concrete building as usual is twice as high, and we can slowly bring it down with some design changes to meet this. So still very applicable in a Brisbane climate. And similar to Jason, I also had a bit of a look at operational and embodied energy, although this is not quite so detailed. This is more just looking at the processing and manufacturing of the material embodied carbon emissions, and then comparing that against operational carbon emission over a 60-year cycle. And we can see that similarly, we can keep reducing this. However, around the passive house targets, it kind of asymptotes out where we get reduced benefit in the subtropical climate for this project. So yeah, that's my main presentation. So we can see that passive house is actually applicable for subtropical and all climates. The CLT needs to be protected from all moisture sources, and it needs to be managed appropriately in the specific climate design. And vapor barriers should be avoided, as we recognize that no seal is perfect and eventually moisture will be able to ingress over time. And any moisture that is able to come into the building assembly does need to be managed correctly, and to ensure that there's appropriate drying ability of that wall system for the high performance building. So when considering the in-moisture and driving rain penetration, this is likely to lead to a better outcome. Thank you very much.
Thank you very much, Marcus, for your presentation. So I'm just going to wait for a few of the questions to come in. So if you've got any questions for Marcus and on the CLT timber, then please send them in now. Before we got to those, I actually had a question for yourself, Marcus. For the high growth thermal analysis, what software package did you use for that?
So I've been using Woofy Pro. Later, probably next year sometime, I'll also be using Woofy Plus to look at the building on a whole building level to ensure that I'm looking at the amount of moisture that's diffusing and taking um, that load that's required to dehumidify the latent energy loads into consideration as well.
Okay, thanks. And one other question I had was, for myself, I'm not really an expert in high growth um, behavior, so
Yep.
moist, uh, moisture transfer. So if you want to learn more about moisture transfer, are there any textbooks or recommendations you have where's best to learn on this topic?
Um, well, Woofy itself has a great forum. Um, So I definitely recommend looking at that, and they have a number of training resources that they go through. So that's a great place to start.
Okay, thanks. So I've got a question for you from Jason. Um, how did you consider a lower permeability membrane on the outside of the CLT rather than putting the insulation inside the CLT?
Yep, yeah. So I have considered that. So that looks to be the optimum solution in Brisbane and a subtropical climate with not as high ambient relative conditions as say Cairns or Darwin, where it's able to the CLT is able to dry out a bit faster. However, in like Darwin conditions, it looks to be that we want to keep the CLT on the outside to try and reduce the amount of moisture that's diffusing inwards.
Okay, thank you for that. I've now got a question from Matt Smith, and that was the vapor barrier of timber was discussed. Do you have any preliminary research on the glues used in CLT?
Yeah, so I did do some simulation of that where I'm looking at the PUR, which is polyurethane glues, and that glue itself it can be considered as a vapor barrier, so it does somehow limit some of the moisture that's coming through. Um, but yeah, just due to the to simplify the presentation, I just simulated it as a homogeneous material. But that is going to be some of my ongoing research.
Okay. Another question, and this is from David Bryan. Have you considered the use of adhesive-free CLT materials such as a Brett staple and the vapor transit of this compared to a traditional glued CLT?
That's a really good question. I've looked at some connections such as dowel connections instead of adhesives, but I haven't simulated them or looked at the hydrothermal performance of them. That's something that's definitely worth looking at. Yeah, thank you.
Okay, another question. This is from Elakir Rajan. How does a CLT building perform in a actual tropical climate or place such as Cairns, for instance?
Yep. So in these climates, it kind of also depends on the amount of moisture gain inside the building as well. So it can differ, and it's always worth doing a hydrothermal simulation to look at that project specific basis. From some of the simulations that I did, it looks like you want to have a higher resistive vapor membrane on the exterior with that insulation on the interior. However, again, yeah, it's worth looking at that on a project by project basis at the moment.
Okay, thanks, Marcus. I just have a question for our attendees right now, which I'm just going to push out to yourselves. And that is simply, have you been or are you actually currently involved in a mass timber construction project? At the Institute, we would really like to get an understanding of what is the number of people who are currently working on projects like this, and if we need to prepare more material for these practitioners. If you have any further questions for Marcus, send them in now. We've probably got a couple more minutes of Q&A before I finish off the webinar with some of the upcoming events that we'll be doing. So I've actually got another question, Marcus, for you, and that's from Marshall Gardner. Would a different species of tree for basswood be better for moisture handling or rot resistance? So is there, for instance, any variability analysis on the different types of wood?
Yeah, definitely. So a lot of the CLT that comes out of Europe and even Australia at the moment, all softwoods. In Europe, spruce is used. In Australia, we use radiata pine. And softwoods, the durability is not as good as hardwoods, and there are some CLT manufacturers that are starting to look into hardwoods being used, like eucalypt, and they do manage moisture a bit better. However, it's also worth considering treatment as well. So in cans, it, it may need to treat the timber using like a CCA treatment, depending on how you feel about treatments being used. That might be a solution.
Okay, thanks, Marcus. So just for people's reference, approximately a quarter of people attending today have actually been involved in or are currently involved in a mass timber project, so thank you for that. I just have one more question to ask, and that is, have you used cross-laminated timber in a recent passive house project?
Um, we are looking at some passive house projects. Oh, well, I was involved somewhat in the Gillies Hall, so yep, I would say yes.
Yeah, okay. That was out to say, Marcus, that was actually a question for everyone attending as well,
Oh,
not
sorry.
just yourself. No, it's
Right.
please don't apologise. Okay, so I'll let that poll run for just another few moments. So I think we're probably done with questions for yourself, Marcus. So unless there's any last ones, but I think we're there. So I would just like to take this opportunity before I get onto the next section of the webinar to personally thank Jason and Marcus for presenting today.